So microservices, another way of referring to them is kind of cloud native. So cloud native applications, because most of the time microservices are running in the cloud. I like to say that they're characterized by two things, that they're, number one, highly distributed, very, very distributed. So no longer are things running on a single machine. Even something like a web application, you've got some of it running in the browser, some of it running on another server, dare I say, many, many servers in the cloud. So highly distributed, that's one of the things. And then the other thing that isn't strictly microservices, but because microservices are deployed in the cloud most of the time, this applies, which is that the environments that they run in are constantly changing. So the microservices have to adapt to that change as well. And so in terms of patterns, you have to deal with this highly distributed, which means that your calls are going over networks, and networks we know are unstable. There's the fallacies of distributed computing. Number one that says the network is stable. Well, the network is never stable. So we have to deal with that. And then also the constant change. So there's a whole host of patterns. And in fact, I have just written a book that is about to go to press called Cloud Native Patterns. That's all about the patterns around microservices and cloud native architectures. So not just purely microservices, but cloud native as well. And some of those patterns are, well, a lot of those patterns are really grounded in redundancy. So what we do, for example, is we take every microservice, and every microservice doesn't get deployed as a single instance, it gets deployed as multiple instances. So if something goes wrong with one of those, or one of those is not reachable, others are reachable. There's also redundancy in the interactions. So when a client makes a request to another microservice as a service, if it doesn't hear back, it might retry. Now, of course, retries bring their own problems in that you can end up with retry storms with too many clients asking for too many things from a particular service. So there's another pattern that we put into place, something like a circuit breaker. A circuit breaker is there to protect the service from being overwhelmed with requests. So there's a whole host of patterns that really, again, focus on solving the problems that extreme distribution and constant change bring in. The most effective approach to distributed systems is, well, as I already mentioned just a moment ago, there's a number of patterns. Redundancy is part of it, things like request redundancy and retries. But as I've been working in these distributed systems for quite a number of years, and particularly with some of the recent advances that have come out with things like Kubernetes, what I found the most core model of distributed systems is the notion of independent control loops. So what we've done in the past is we built up an application by a series of instructions that spanned a whole bunch of different systems. So if I was building a web application, let's say, and I needed to aggregate things from a number of different microservices, I would take in that initial request, I would make a request to a downstream microservice, get that back, of course, using things like retries and circuit breakers, make another downstream request, get that back, et cetera, et cetera. And that is difficult because you end up with so many dependencies. So one of the examples I like to use is that Netflix, the Netflix homepage, is when a request goes to that web application, the Netflix homepage, it results in a series of downstream requests, hundreds of downstream requests. And in order to render that homepage, all those downstream requests need to operate at some level. So that's a lot of coupling. If instead we take an approach where we say, let's break that apart and say each one of those pieces is responsible for its own world and has a control loop that's operating independent of the other control loops, then when a request does come in, a lot of independent processing has already happened. At the core of that approach is that we have to shift our thinking from kind of a request response over to event-driven. So it's really control loops and an event-driven approach. So very well put. So we went from a physical to a virtual world. That transition was really largely about creating optimizations at the IT level. So being able to have multiple virtual machines on a single physical host and those types of things. Containerization brings some element of that. We sometimes call that bin packing. So we can bin pack more containers into a host than maybe we could virtual machines. So there is some benefit, some cost benefit to that. But really where containers became very prevalent and really provided a lot of value in IT was around dependency management. So it's the old adage of a developer hands over their code and says, I'm done, and the operator installs that on their system and it doesn't work. And they say, hey, you darn developer, your code doesn't work. And the developer says, well, worked on my machine. And it's because what's on my machine is different than what's on the IT machines, the production system machines. And so that was the initial benefit that we got from containers, was that we had the ability to bundle all of those dependencies up into a container image. And now we just have a runtime for container images that doesn't have any external dependencies. Really the only external dependency is a kernel, an operating system kernel, and the containers run on top of that. What's emerged beyond that, and that's been fairly well understood for a couple of years, but just like anything else in this evolution to microservices and cloud native applications, it brings its own challenges. Because I remember quite a number of years ago when people were really excited about Docker and they'd say, well, my developers are just going to hand me Docker images and I'm going to run those. And I'd say, really? Those images that you're going to trust the developer that there's no vulnerabilities, that they've got the latest version of the software. And when I posed it that way, they would say, ah, right. We still have all those enterprise concerns of security and compliance and licensing and all of those things. I need to make sure that I'm running licensed software. So what's happening now is that there's an understanding that the container image needs to have a certain amount of control built into the process of creating that. And the great thing, though, is that, especially if you have certain types of platforms, you can leverage a platform to allow a set of individuals who are concerned with those enterprise controls, like security and compliance and licensing and so on, have them responsible for building a part of the container image and then allowing the developer to build that other part of the container. Once you have those container images now, because you have everything bundled up into a single deployable artifact that, quite frankly, deploys in microseconds, very, very fast deployment, that affords us the opportunity to, for example, address that constant change of the cloud that the cloud brings with it more effectively. So when a host changes on the cloud, no problem. We can take that container image and we can spin it up on another host in a matter of just a few microseconds. So there's a whole host of both challenges and opportunities that come from containers. Again, a very, very good question. So emerging tech is an interesting thing because we can get very distracted by the shiny object. So something new comes along and we jump on board right away. I spend a great deal of my time influencing our product strategy at Pivotal. I always like to say that product strategy is really driven by three things. It's driven by what the customer is asking for, so generally an existing customer, and they're usually asking for incremental improvements over what you have. The second thing is engineering feasibility. So if a customer, for example, or I myself as a product strategist am asking for something completely crazy that can't be done by the engineering team, then that's something that has to be considered as a part of the product strategy as well. And then the third element, where I spend most of my time, is really what's happening in the market. And that might be competitive, but in the things that really excite me are, what are the market opportunities? What are the new technologies that are coming available on the market that give us an opportunity to do something very new and innovative? Now, how you choose those things, how you choose what to invest from the market and what you don't, requires quite a bit of discipline. On the one hand, I see many of my colleagues sometimes, we get very distracted by the shiny objects. There's something new that's coming on. And so, for example, that shiny object a number of years ago was Docker. Now, at the time, I'll tell you personally, anecdotally, that Docker was interesting, but really it was difficult to assign that to business value. And that's the real key. The way that you can choose what you want to invest in from an emerging technology perspective is that you have to go through the exercise of saying, this is a new technology, but what can I do with that new technology? And so really trying to tie that technology to business value. You form some hypotheses, and then you start to vet those hypotheses against some stakeholders. Those stakeholders might be existing customers, but it might be the customers you don't have yet as well. The other thing is, of course, to come to events like Codemotion and explore those hypotheses with a number of individuals. So I think that's the real key, is to form hypothesis, be disciplined, and make sure that you vet those hypotheses and always, always, always tie it to business value.